Well, welcome to Geology, everybody. How we doing? Let's look at earthquakes a little bit. I'm basically going to shoot through a bunch of Chapter 12. I didn't make a separate note sheet. There doesn't necessarily have to be a ton of me right for this. But check out your textbook, your online textbook, Chapter 12. And I have the PDF version here in case you're using the other one. 1989, I would have been, 12, 13. Watching the World Series, this happened. Now, I'm not going to try to play it through this video because that gets complicated. I'll post this separately in the thing. And watch it, check it out. It's not mandatory, but check it out. I think it was the first time an earthquake would have been broadcast live on television. And I remember watching this as a kid, and trying to get ready to watch a little bit of baseball. My mom let me stay up late, and an earthquake interrupted the very beginning of the game. And for all the coincidences, for all the rarities that happen, how rare are earthquakes anyway? Major ones. Another coincidence is that this World Series happened to be two teams that were in the same city, Giants and the A's, just across a bridge from each other. They actually credit that with saving lives because with the game about to start, you either had a large portion of the town there already at the game or at a bar watching it or with their family watching it, who knows. But the volume on roads was actually lower than usual for the time that it happened, and they're thanking this game where two teams in the same city were playing against each other. This was a 2-level highway. So like the top deck would be going one direction, the bottom deck would be going in another direction, and it completely pancaked as a result of that. But again, with volume being lower, and I'm not saying there were zero fatalities, volume being lower on the highways, there was less than there may have been had that happened at any other moment other than right at the beginning of a World Series game. So, it had a big impact on me. I've only felt one earthquake, and I was in Oswego. It was spring of 2002, and it was up towards the St. Lawrence River, and it was barely recognizable. So I've never really been in a serious one, and I don't mean to speak light of it. Obviously, it's can be a very, very rough, sad situation, right? So let's look a little bit at the geology behind them, right? And go forward with that. Now, it's amazing in my lifetime, this clearly had an impact on me. Lo and behold, I got the job that I did. Watching this was a major impact on me as a youth, but to see technology evolve from this to this was just this last week that there are skyscrapers that have these big masses in them to stabilize buildings. It's such from 89 till now, it's my lifetime. I know I'm a little older, but it's not really a long, long time to see the difference in how we can engineer our way out of these situations should we all educate ourselves and understand them. It's remarkable. So this is actual footage from just a couple days ago, this earthquake taking place in Taiwan and the building being just fine. So looking at earthquakes, what do we want to do? Let's talk about elastic rebound first. So elastic rebound theory, which this is a model of how some teachers might teach us in class. If you take a brick, something heavy, and you put sandpaper on the bottom of that and have a strip of sandpaper here, and you pull on something elastic, like a piece of bungee, you can pull and pull and pull and pull. And because of the two pieces of sandpaper on each other, not much happens. But eventually you get to a point where there's enough stress on that, strain on that elastic that it slides. And then, you can measure this. This is a lab you can do. It's not fantastic. There's limits to it. The faults in this case don't exactly go like that. There's limits to this model, but it's not too bad at just a visualization of how elastic rebound theory works. In the rock, same idea. Take rock, no stress. It's happy. It's doing its thing. If you put stress on it, in this case where it's shearing, that can build and build and build. But the elastic idea of elastic rebound theory is if you were to wave a magic wand and get rid of that stress, the rock could recover. Have it continue to build and build and build and build. And like the brick in the previous example, you get to a point where they got no choice but to go sliding past each other. Sometimes I've got these big heavy lab tables in a lab room, like most science rooms, right? What I'll do is put a little tiny Simpsons guy, little plastic toy there, and slowly push on the table, and it doesn't do much, but finally, once I put enough pressure on it to move it, it slides. Now, it's just a table shaking. You can hear it in the room. Usually that little dude falls over. But that's kind of the idea. If this happens to rock, what you got to remember is that we are tiny, 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 tiny little organisms on this great big planet. So that bit of shaking on the table kind of simulates what would happen that happens in the rock. Everything shakes, and we insignificant humans and the insignificant bridges and buildings that we try to build, that shaking's for real. It's big time. You know what I mean? I really like this diagram here because they show like, okay, what if we were to like microscopically zoom in and see that it's not two smooth pieces of rock. Rock's jagged and got all these little nooks and crannies. So that might be what grips. But as that pressure builds and builds and builds and builds, it eventually gets to a point, again, elastic rebound theory, where it gives, it slides. And that shaking is what we have to deal with here on the surface. Right? Throw some vocab at you. Again, we're right out of the book here, so just check it. Epicenter and focus. So the focus or hypocenter is within the Earth, down deep where that rupture would occur. Here they color code for where the biggest slide is, and therefore probably the most energy release. But it's finite. It's not going to be like, this is why we can say this earthquake happened here. If something happens, it's not like the whole of the San Andreas Fault all the way across the majority of California all slides together at once. It does it in little sections. So we'll say that's where the energy is coming from. On TV, when they got to say, where was the epicenter? That's the spot directly above it, up on the surface. Now, if you've heard of like aftershocks, or the idea that this can lead to others, take that same kind of nebulous blob of rupture here, right? But consider that when that happens, that might put more stress on other areas near it, which then can result in maybe aftershocks. I suppose maybe even ideally aftershocks, right? If small ones happen as a result to kind of just correct for all the stress that's suddenly added to different spots, that's better than maybe the case of this leads to a significant amount of stress on another that continues to build until that slides again, giving us another larger earthquake. But yeah, so just keep in mind, it's not the whole entire piece at once. It happens in areas which may cause different areas to react differently. So one of the ideas up in the Cascadia area, I'm going to open up Google Earth real quick. So this Cascadia area, which should look familiar. We've come to this a couple times by now in our little lectures, where this small plate is sliding underneath the Pacific Northwest, Washington and Oregon, and earthquakes and volcanoes are certainly a result of that. Hey, oceanic, continental boundary, as long as we can do a little review here. But where are areas where it's really stuck? And that can be maybe the bad news. If this area is just stuck, just not moving, that doesn't mean that the pressure's stopping. Where it gets a little warmer down here, it may slip a lot easier. But that's going to just add to the pressure that's happening up here. So where is it that maybe the severity of these things is worse because the frequency is less, which lets more and more and more stress build and build and build and build. And when they happen, and it will happen, whether it's once humans cease to exist in Washington and Oregon are no longer a thing, or if it's tomorrow, it leads to some sad scenarios. The Japan one recently, certainly evidence of that. All right, so I'm going to skip around. I'm going to go in a slightly different order than the book did. I want to go down to page 14. Let's talk more about plate boundaries, right? So how did we figure this out? I mean, I think this should be kind of clicking if you've done all the videos till now, that the locations of earthquakes have done a really good job of delineating out where these plate boundaries are. So again, let's consider us in Oswego. If we're going to stay in Oswego, we're in the center of that North American plate. We're in a pretty safe area. Yes, there are some random smaller intraplate earthquakes. They happen up near Quebec. There's some down towards it's called New Madrid down Missouri. There's some. Take a big plate and try to put it over around Earth, and the different small stresses will add up and give you earthquakes. But look, the majority of them are happening, and the severe ones are happening at those plate boundaries. So they've helped us delineate it. They've helped us map and figure out how all of this works. It's indirectly observing all of it by watching earthquakes and plotting earthquakes. So this one, I made reference to this early when we talked about, let's go back to Google Earth. When we talked about the earthquakes down here, where this plate is subducting underneath South America, we talked about the earthquakes being at shallower depth and then intermediate and then deeper, and using that idea to like figure out what must be going on with that tectonic plate that we can't see, that tectonic plate that was the bottom of the ocean underneath South America. We're not going to be able to directly observe that. There's nothing that can down there. But by watching the earthquakes and how they move, we have figured it out. Just since we're reviewing oceanic continental convergence, or come up here to the Aleutian Islands, oceanic convergence. So that whole chain of volcanic islands, that volcanic island arc, is caused by the same idea. And again, the book does this great diagram of saying that your earthquakes, not perfectly, but have a pretty good trend of being the ones that we've coded in pink, and then white, and then green as you work your way back. As that plate comes up here, subducts underneath, and dives down into the earth underneath the crust over there. The deepest earthquake should be the furthest away. That cross section that we did, probably video 4 and 5, is key to understanding that how that plate subducts and dives down underneath when it goes. That depth of earthquake thing mimics that pretty well. All right. And yeah, I mean, continent to continent, they're happening all over. That's like the car wreck one where the cars are the hoods are getting crunched up. All right, did that. Let's go back up now and talk about waves. Back up to page 7. I mentioned this. When was it? It was pretty early in this unit too. How did we figure out, and this question could pop when we do the segment exam, how could we figure out what's going on inside the Earth? How do we know this inner core, outer core, asthenosphere, lithosphere, mantle, all of that? We've done it indirectly by observing earthquake waves. And I said at that point, hey, there's a thing called a P wave and there's a thing called an S wave, trust me. So now let's unpack that just a little bit and like figure out what's going on. So if we could all be together, I would do almost this exact same demo. I've got a big long slinky. You take it, you stretch it across the floor, and what you can do is just give it a quick shove like that. And if you do that, you'll see that wave propagate forward through the slinky all the way to the far side of it. That's how a P wave works. It's compressional. And P being P, hopefully it says primary here somewhere. There we go. They're faster. They're going to get to places first. They travel faster. So the earthquake happens at that exact moment. Both P waves and S waves leave. The P waves go faster. So they're going to arrive places first. And they're called primary. S waves would be, you can take either that spring or take a piece of rope and like whip it up and down, whip it up and down, whip it up and down. And you see that kind of wave. So what it relies on, this is kind of like how a sound wave works. This will travel forward because molecules bang into each other and send that energy forward. This requires, for the shear wave, it requires that the thing wants to snap back. This is the reason why S waves do not work in liquids. I don't know if that's a thing it says down here too. I did read this. Maybe it doesn't. So these do not travel through liquids. That's when, again, back to tectonics, when we talked about that, what's going on in that outer core, we figured out that it's a liquid because the S waves do not travel through. Liquid with a big slash. They don't work in liquids. A liquid does not want to like snap back to place. So these are completely absorbed by that liquid outer core. In fact, that's how we figured out that we have a liquid outer core, because when both P waves and S waves hit them, S waves just stop. So that's our explanation for what's going on down there. And they're slower. So the two things we want to do with these kinds of waves, slower shear waves, faster compression waves, is figure out how can we use that to figure out how far away an earthquake is. And probably mention real quick that that's not necessarily the waves. I don't tend to hammer these too hard on quizzes. But when they interact with the surface, then this is what is going to cause what you would sense, or what happens to a building, are these types of waves caused by the interaction of those types, the P waves, the body waves, to the surface. They call these our body waves going through the body of the earth. But how can we use them to figure out how far away an earthquake is? And then we'll talk about the scales real quick and we'll wrap this thing up. Thanks for sticking with me. So if you've ever done this is a common thing. I did this the other night. If you've ever done the thing where you see lightning and then you count like 1 Mississippi, 2 Mississippi, 3 Mississippi, and wait till you hear thunder, and use that estimate to say this is about how many miles away that thunderstorm must be, this is what you're doing. This might look more complicated, and I guess it is a tiny bit, but in principle, it's the same thing. What you do with that sound and light thing is you know inherently that light goes a lot faster than sound. Also, if you've ever seen a firework from a big professional fireworks show that go way up there, you can see it before you hear it because light is faster. You could actually use that difference in time to figure out how far away it must be. Because if that thing went off right next to you, it would be like flash boom, right? Whereas if it goes away goes off miles from you, you'd see the flash and then you have to wait, and then hear the boom from it, right? Just take that concept and do the same thing. Since P waves go faster, they're going to arrive places first. Since S waves go slower, they're going to arrive places second. But the further you go in distance, the more like opportunity there is for them to get further and further and further apart. So yeah, just like estimating for thunderstorms, but we can do it very exactly. Now I'm not going to have you actually do it, but conceptually, I'm going to throw some of this stuff on there to say that what happens as you increase distance, the arrival time between P and S is going to continually increase and increase and increase. So if you lived in San Francisco in 1989 when that earthquake went off and you had a seismometer in your closet, as we do, like they would have been like right next to each other. It would have been P wave, S wave, right? But if you had one here in New York that could pick up those waves, it would have been P wave. Then you got to wait and wait and wait and wait because that slower S wave has taken longer and longer and longer to get there. The further they travel, the bigger that gap gets. And that can give you an exact distance, right? Which is kind of useful for figuring out where an earthquake is, but not perfect because it gives you a distance. So if I were to say, great, this earthquake is 1,800 kilometers away from where I live, from my seismograph right here, right? It's like, cool, well, okay, 1,800 kilometers, but in what direction? Where? That would really be like a circle. If I live here, you go 1,800 in radius, it could be anywhere on that circle. So not super useful on its own. But if you do it with 3 separate stations and get those circles for 3 separate stations, you can triangulate and you can get the exact location of where it should be and locates the earthquake that way. So your minimum is 3. They do it with more and they can get more accurate. They can figure out more things. Excuse me. But without 3, as a minimum, you're not going to get it down to exactly where it's got to be. All right. Well, so we'll just do a quick wrap up on how do we measure these things. They can measure, like they showed the thing right here, right? And I've got one on my wall. I don't know if it's worth getting down because I don't think it'll show up very well on the camera. That when one goes off, this is an extremely simplified version of how these things work. If it's like gimbaled, so it stays still in space while everything else moves around it, it will record what the movement is just with a simple pen. That's a really simplified, broken down version, but would functionally work, right? So you get these readouts for earthquakes, and then we get into saying, how big are they? So if you've ever heard these numbers, and maybe you've heard the term Richter scale, which is slightly outdated, we'll talk about that. That's how we measure how big these earthquakes are going to be. All right, so you can measure the amount of shaking just very literally on that, right? So getting rid of Richter, we call this the magnitude scale. So if you've heard of magnitude blank earthquake, in fact, let's look up that Taiwan one and see how big it was just the other day. So here we go, magnitude 6.9. So pretty strong. So what does this mean? And again, Richter scale is not something that's used. So on the scale, it's a logarithmic scale. So this is going to be a little bit strange if you haven't dealt with this before. We're kind of intuitively used to linear scales where you go from a 2 to a 3, you go up by 1. You go from a 3 to a 4, you go up by 1. You go from a 4 to a 5, you go up by 1. That's not how this works. This works so that each step is significantly more than the step before it. So if you go from a 3 to a 4 and just say that's some amount of increase in what was detected at that meter, right? Going from a 4 to a 5 is not that same increment up. It's like 32 times the increment up. Which means once we get up talking 7, 8, 9, it's getting pretty serious. 8 and up is certainly disastrous, depending on the population centers that are near there. But what we'll want to get, and I guess most basic way that I ask these questions is, what does that scale, what does that magnitude scale actually do? It's an actual literal measurement of the waves and figuring it out with mathematics at that center. And then you can go and throw it on the internet and say, we've researched it, we've run the numbers, and it's magnitude 6.9. And it's that. I'm in Pulaski, New York. I look at this and it was a 6.9 earthquake. Right? The other scale that's sometimes used describes its intensity based on observations. Nothing that's like numerically measured necessarily, but how is it felt? And the thing with this one is that that is dependent on your area. So what did I feel in upstate New York from this earthquake in Taiwan? Nothing, right? If you were right there in the middle of it, you would have felt something significant. And as you go further and further and further away, it decreases and decreases and decreases. So this scale, modified Mercalli, is more based on like observations in your local area where you are. So you'd expect those, nice. I was hoping there'd be one of these. You'd expect those to be the highest near the earthquake and then tail off as you get further and further and further away. Check out those descriptions, give it a quick read, and that will, you'll read it. You'll see the differences between that and something that's a mathematical calculation of the amplitude of the waves. All right, that's most of what I wanted to hit. Check these. There's questions and answers at the ends of these. It may not be a terrible idea. We didn't talk about liquefaction. I didn't want to talk about that. So why did this bridge collapse like this? What can happen is that you can have the effects of waves amplified in certain scenarios. Sorry, that's our bell here. You can have the amplification of the effects of the earthquake based on what is going on your subsurface, particularly if it's like wet and sandy. That does this thing called liquefaction, where with some shaking, this little demo is great for it. I've set this up on a table and everybody pound the lab desk as much as they can. Wet sand, when those particles start shaking, that water can start to work its way right towards the surface, and then it loses any structural integrity it would have had. And something built on top, a rock or an apartment building, is going to just kind of bubble right down within it. Severe stories of this, anecdotes have like people being sucked right into the ground from it. It can be a very, very, very strong effect. And that is when this bridge took place in 89, bridge collapse took place. That's what it was blamed on. That this was on a specifically kind of sandy area. If you look at subsurface maps, where that water came up, pillars got shaken enough that the upper deck with that weight collapsed right down in. Another thing might not be in here. I want to draw it real quick. Give me a sec. Another thing that can happen is, what is the subsurface like? So if we had a mountainous hard area that kind of fades off and has more mountainous hard areas over here, this is kind of what happens in San Francisco. And then there's inside of that, there's softer layers of sediment. And then in that case, even inside of that, there's San Francisco Bay, right? So geologists weren't necessarily in charge when people decided to put in cities, right? San Francisco is a great location for all of the reasons why it was put there: shipping, transportation, commerce. There was nobody to say, "Oh, guys, everybody, this isn't a great idea. There's a fault here, and it's sitting on soft sediment surrounded by rock." And what's happened since then, like in New York, they've built out retaining walls and then backfilled it. In the case of San Francisco, with bayfill, so they go down here, dredge out soft sediment, build a retaining wall, and backfill. I mean, real estate's so valuable there that it's worth it to do that and create more land, right? Well, what happens then when we get shaking is that the shaking in the rock, let's say it has some value, right? That gets amplified by all the soft sediment that's in there. A cheesy example I use for this or demo is if you have a bowl of Jell-O sitting on one of these lab benches again, and you shake the table, the bowl shakes about the same amount as the table, but picture what's going on the Jell-O inside. If you put a little Monopoly house on that and it's shaking, that thing's gonna be going a lot harder than the rest of the table. If hopefully it's not too silly, but that's kind of the example of how this works. That the softer stuff inside of the crater of harder stuff will amplify that shaking in softer sediment. So it's like, triple whammy for San Francisco. It's a tough spot. All right. Thanks, everybody. That was a lot of rambling. Where's the text? I think we got through everything. That was a longer one. I appreciate you sticking through it. We'll talk to you soon.